So I'm going to talk about higher order beliefs in game theory, some material about higher order beliefs in game theory. Something that I always like to start out saying is to point out that for the first few decades of game theory through the 1960s, it was a consensus among economists and game theorists both that game theory was not a particularly useful tool for applied economics. Why? Because game theory, you had to describe the game. So in modern words, we might say there had to be common knowledge of what the structure of the game was. The language then was complete information. Thank you very much. So that was the long title of the lectures. So they called that complete information, and there wasn't complete information. You couldn't describe the whole game, so game theory was pretty useless. That was the general view. And in particular, part of this view was that higher order beliefs should matter. You know, in practice, they knew that you didn't know exactly what the game was, so there should be uncertainty about what other people were thinking, uncertainty about what other people were thinking you were thinking. So higher order beliefs should matter. Now, at some point, there was a switch. We came to believe that actually there was absolutely no problem applying game theory to economic problems. Part of that change was due to the insight, the important insight of Hassani, formalized by Mertens and Zamir, that although there wasn't common knowledge of the structure of the exact game that was being played, if you imagined a rich enough description of players' incomplete information and you modeled it with a type space, that was kind of an innovation of Hassani, you can model it with a type space, you could make the type space as rich as you wanted and you could capture all kinds of stuff. Okay, so, and then the economics profession at some point thought, oh, that's great. No longer is there a conceptual problem because there isn't common knowledge of the structure of the game. Let's just go back to assuming some very simple common knowledge assumptions about the game being played. So they didn't really, they sort of forgot about the underlying issue, which is that higher order beliefs should matter, and we didn't talk about it. Okay, so so I'm starting off my talk with a slightly rambling introduction, history, context, because that will organize the material that I'm going to talk about today. So an important insight was due to Ariel Rubinstein wrote a paper called The Electronic Mail Game. To read the paper today, you have to understand that electronic mail was an exotic title at the time. Nobody used electronic mail except for Ariel and a couple of other people. But it was a metaphor to describe the problem. Okay, so Ariel introduced the electronic mail game, and I'm going to describe it to you in a few minutes. But the insight that came out of that game was that game theory offered very different predictions between when there was complete information or common knowledge of payoffs of the game and the situation that Ariel called almost common knowledge of payoffs, which was that everybody knows the payoffs, everybody knows that everybody knows them, and so on, up to an arbitrary number of levels, but not common knowledge. Okay? So that was a lesson that is offered by this example, which has now been used many times. So this game illustrated the extreme sensitivity of economic outcomes to higher order beliefs. How to interpret this observation? Ariel's interpretation, this is a paradox. The message was that obviously, if you had high numbers of levels of knowledge, you would behave as if there was common knowledge. You kind of took that as given. Many other people take it as given, as a behavioral assumption. But this was just a paradox of our models, and we had to adjust our predictions appropriately. I had a different reaction, as did my co-author, Hyun-Sung Shin. We kind of thought that higher order beliefs were kind of important. They mattered in practice. And we thought we took a different view, which is that, these higher order beliefs that people seem so worried about in the 50s and 60s actually mattered. And the email game was a demonstration of, was a formal, logical demonstration of how they could matter. And this was an interesting thing to study. Okay, we wrote a paper in 1998 called Unique Equilibrium and a Model of Self-Fulfilling Currency Attacks, which was very self-consciously designed to write a model that would be an applied model that would fit with applied economists' way of thinking about things, but that was making higher order beliefs matter somehow. During the course of writing it, we became aware of a paper by Carlson and Van Dam on global games, a brilliant paper by Carlson and Van Dam on global games. If you read our paper, we hadn't completely absorbed it at the time that we wrote it, but anyway, so our paper can be seen as an application of global games as we would now define the field. And applied economists did take some interest. They took some interest. They still take some interest. Maybe I'll talk a little bit about how applied economists have taken an interest in it. Okay, however, forget applied economists for a second. The email game does suggest a theoretical question, which is the email game, as we will see, illustrates the fact that strategic outcomes can be very sensitive to players' higher order beliefs. That begs the question, are all outcomes sensitive to higher order beliefs, or are some not sensitive to higher order beliefs? So which equilibria are not sensitive to higher order beliefs? Okay, so with Atsushi Kaji, I wrote a paper on robustness to incomplete information, which was basically that question. It was a response to the email game saying, the thing that happened in the email game, when can you stop it happening? What's the... Now, there's been a literature on robustness to incomplete information. Satoru Takahashi, Daisuke Yoyama, Takashi Ui, who was here yesterday, I think he'll be here tomorrow. Lots of famous Japanese economists have studied this topic. So let's think about it as a Japanese economic theory topic, robustness, incomplete information. We're publishing a bunch of papers now in the Japanese Economic Review. So it's definitely, and it's less applied. It's seen as a more niche theory topic. One thing that will come across today is that it is, so we've always known that it's closely related to global games, and that will come out in my lectures, hopefully. In fact, there is I recommend to you a book which I love by Rani Spiegler, who has appointments at the University of Tel Aviv and at University College London, called The Curious Culture of Economic Theory, which is a kind of cultural analysis. And he has a whole chapter, basically making the observation that global games people treat as applied economics. This is something that applied economists map into problems that they study, whereas the email game is just a theoretical paradox that wacky theorists go study. And yes, I think he's correct in his analysis of how the profession sees it. To me, I think it's just fine. That is, I think it's good that we're connecting with applied people, and if global games as a way of formulating things happens to do it, that all the better. But it is closely related to the more abstract theory topic of robustness to incomplete information, which I will highlight today. Okay, here's a little bit more context. In the 1990s, Mondra and Shapley wrote a paper about potential games. These were games which have the feature that the players' payoff differences so the payoffs differences, so the change in a player's payoff, if he changes his action, given some actions of other players, are the same as what they would be if they had a common payoff function, which we call the potential function. Those are potential games. Interesting class of games. They've come up quite a lot since Mondro and Shapley wrote their paper. I mean, they came out before Mondro and Shapley wrote their paper without that name, but important idea. Takashi Ui, in the Japanese tradition of robustness and incomplete information, wrote a paper showing that potential maximizing equilibria are robust to incomplete information. Okay, so yeah, I'll come back. I will explain this in due course. We later, so with Takashi, we later wrote a paper in which we came up with some more general sufficient conditions for robustness to incomplete information. There were further papers developing more concrete sufficient conditions for robustness to incomplete information. An important paper in my mind in this literature is the paper by Professors Oyama and Takahashi in 2020 in Econometrica, in which they show that an example of a generalized potential maximizer, so a monotone potential maximizing equilibrium, which I will tell you what it means in due course, they showed that within the class of binary action supermodular games, which may sound a tiny bit special to you, but I want to suggest is actually a pretty big class in terms of the economics that's captured by it. Within the class of binary action supermodular games, being a monotone potential maximizing equilibrium was not merely sufficient to be robust to incomplete information, but also necessary. So that was a big deal. Okay. Okay, something else that has been happening that you may have noticed in theory is that the last, what are we talking about now, 15 years at least, the last 15 years or so has seen an explosion of theoretical work that has studied Bayesian persuasion, or more broadly, we might call it information design, studying problems in which you have a designer who can choose the information structure and can't change the game, but can choose the information structure in order to affect what outcomes occur. Big literature. I've been a little bit a part of it, thinking about it. And in this literature, my work, like everybody else's work, like most other people's work, did the usual, proceeded with the usual mechanism design methodology of saying, well, suppose you can design the information structure, but when you design the information structure, you can also, you assume, you're optimistic, you think that the players will play the equilibrium that you want them to play. Okay, so call that information design with benign equilibrium selection. Okay, you get the equilibrium that you want, usual mechanism design assumption. That's what we do. You get the revelation principle. That's the whole beauty of it. Great. Okay, but a small number of people started posing the question, suppose you do information design, but you have adversarial equilibrium selection. That is, you as the information designer, you get to pick the information structure for the players in order to induce the outcomes, that you want. That's great. But the bad news is that the players get to choose what equilibrium they play. And suppose now that we had a more demanding information designer who wanted to make sure that whatever equilibrium they ended up playing, he got an outcome that he liked. Okay, so information design with adversarial equilibrium selection is what happens if you insist that every equilibrium delivers the right outcome, which is analogous to the full implementation literature in mechanism design. Okay, so given that I was writing a bunch of papers in this literature, and given that I've written a bunch of papers on robustness to incomplete information, I'm kind of embarrassed how long it took me to realize that actually information design with adversarial selection is very closely related to robustness to incomplete information. Okay, and I later wrote a paper with Professors Oyama and Takahashi, which is really building on their earlier robustness paper of 2020 to give the best results that we know about on information design with adversarial equilibrium solution. Okay. Okay, so that's an overview of a bunch of material. I haven't taught this material for 20 years. I'm on sabbatical at Yale this semester, and I was inspired by Professor Oyama's 2023 topics course at the University of Tokyo, and decided to do a half semester second year PhD course on roughly the material that I just talked about to you. And actually, I have a topics course at MIT next year, so I'm going to teach it again to them. And as I try to do with these courses, I try to emphasize some open questions. So it's been quite exciting for me. I don't know how useful it is for the Yale students to revisit this material, because it makes me think about how it all fits together and what I think about it, and things have changed, actually. My views of lots of things have changed, and so it's been fun. And then coming to Tokyo, I was asked to give a couple of lectures. I thought that what I would do is just give the half semester course, but talk very quickly. So that's the plan. Not quite. I'm going to give you a few highlights from the course. It's going to be a little impressionistic. I'm not going to do too many detailed arguments or detailed statements, but I'm going to expand on some of that discussion that I gave you and hopefully give some hints on what I think are exciting open questions and where the literature is going. Any questions? All right. Let's start with potential gain. And one reason I gave that introduction is because the order is a little funky, and I'm going to present the material. Okay, potential games. Let's talk about potential games. So let's start off with a complete information game. For a complete information game, I'll say there's a finite set of players. That's supposed to be a capital I. And I'll use I to represent not just, I'll abuse notation by having it represent not just the set, but also the number of players, capital I. Okay. Each player has a finite action set. You write A for the product of the action sets. Each player has a payoff function, obviously. So holding fixed the players and the actions, the game is parameterized by the payoff function. So this bold G is how I describe the complete information game. Okay. What about potential maximizing equilibria? Well, a potential function, which we will sometimes interpret as a common payoff function, it's as if there's a common payoff function V that players have, is a mapping from action profiles to the real line. I will say that V is a potential function for complete information game G if there exists some weights, one for each player, strictly positive weights, one for each player, such that the payoff difference for player I of switching, payoff gain from switching from action AI prime to AI, given some profile of actions of other players, is actually the same as what it would be under this potential function or sort of pseudo common payoff function we can put in a constant here. Okay, so Mondrian and Shapley actually called this weighted potential games if you use the weights, but the weighted version is the relevant one, really. Okay. Now, a pure strategy profile is a potential maximizing equilibrium of the complete information game G if the game has a potential function V and the potential function V is maximized at action profile A star. Okay, now the thing you have to remember, you have to be clear about, is that if an action profile maximizes this sort of common payoff function, then it will definitely be a Nash equilibrium. Okay, it will be a Nash equilibrium because nobody will have an incentive to deviate by these conditions. Okay, however, it's important to remember that a game that has a potential may have many Nash equilibria. Okay, Nash equilibria say that no individual player has an incentive to deviate by switching his action. Okay, so intuitively, a Nash equilibrium is like a local maximizer of the potential function. Changing one dimension of the action is not going to improve the potential function, but moving many of them might. Okay, so think of potential maximizing equilibria as global maximizers of the potential function, and Nash equilibria, non-potential maximizing equilibria, Nash equilibria, a sort of local maxima of the potential function. We'll give an example. We'll give examples in a second. Okay, so Mondor and Shapley introduced this potential game language, and they wrote that the existence of a potential function raises the natural question about the economic content or interpretation of the potential function. What the players try to maximize, they say, because, you know, you could think of them as maximizing the potential function instead of their payoff functions if you want. We do not have an answer to this question, they say. However, it is clear that the mere existence of a potential function helps us, the analyst, and the players better analyze the game. So basically what they were saying was potential games have an interesting structure, but you shouldn't jump to the conclusion that people will play the potential maximizing equilibria. Let's remember, they were writing in the 1990s. You weren't there, but I can tell you that the 1990s was the tail end of the era where game theorists were obsessed with finding the right refinement of Nash equilibrium. If there was something that selected among Nash equilibria, people went crazy. Okay, but they were careful. They were saying nothing about this proves that they have to be the thing that you focus on. Although they did note a couple of things. They noted that recent experiments on coordination games that they described, actually work by Battaglio et al., favored the potential maximizing equilibrium. There were a bunch of experiments on minimum effort games, and they pointed out that the experimental results suggested that the potential maximizing equilibrium actually was played. Okay, I'll come back to experiments in a little bit tomorrow. And they also pointed out that potential games have a bunch of nice properties if you think about learning foundations of Nash equilibria. So, you know, they were careful not to say that it was a refinement, but they sort of suggested that maybe it might be a useful refinement. Okay, well, let me just illustrate potential games for you by considering the special case of two-player, two-action games, which are going to be important in my lectures. Suppose that we have a two-player, two-action game. So a general payoff matrix. There's 8 numbers we've got here. Okay, make up the payoffs of the game. Further, let's assume that there are two distinct strict Nash equilibria of this game. So it's a coordination game. Without loss, let's assume that UL and DR are the two strict Nash equilibria. Okay, of course, that puts restrictions on our parameters. A is bigger than E, G is bigger than C, and so on. Okay. Let's think about this class of games. The payoff gain, so remember the definition of a potential gain was all about what are your gains from switching action. So the payoff gain to player 1 of choosing U instead of choosing D, he gets a payoff of A instead of E, so A minus E is his payoff gain, and in fact it is positive by assumption. So if player 2 chooses L, his payoff gain of choosing U rather than D is A minus E. Whereas if player 2 chooses R, his payoff gain is C minus G, which under our assumptions is negative. Okay. Good. Well, now we can check if you put enough probability on your opponent, on player two, choosing L, you will want to choose U, but how much probability do you have to put on U in order for up to be a best response for U for player one? Well, you can check, do the algebra. It's G minus C over G minus C plus A minus E. Why is that the case? Well, G minus C times A minus E is the what you get if player two chooses L, and C minus G times A minus E, so one minus this, you're going to have an A minus E on top, is what you're going to get if player two chooses R. Those two terms are going to cancel out. The net effect is going to be zero. So that's the probability that will make you indifferent. Don't worry about the algebra. All right. And we can do the analogous calculation for player two. There's going to be a critical probability at which playing L is the best response for player two if he puts probability at least P2 on player one choosing U. Okay. Now, as part of this 1980s, 1990s obsession with refining equilibria, Hassani and Selton wrote a book whose purpose was to define, it was going to give a selection of equilibria in any game. It was an ambitious book, what can I tell you? But what they had was, in the particular context of 2x2 games, they had a particular prediction, which they called the risk-dominant equilibrium, which in this notation corresponds to P1 plus P2 being less than or equal to 1. They had an axiomatic foundation for it. They also had a more complicated procedure for more general games, but we don't worry about that. Nobody else worries about that. But the risk dominance is an important concept. Okay, so this was the condition. Okay. And clearly, there's something good about being the risk dominant equilibrium. There's a larger basin of attraction. There's more probabilities at which you're going to want, if I allowed for there to be uncertainty, allowed for strategic uncertainty, I allow a richer range of strategic uncertainty in support of that equilibrium. So sorry, this is a misstatement. What the P1 plus P2 here corresponds to the relevant probabilities for the equilibrium UL. So this should say, Hassani and Selton said that UL, that equilibrium, was risk dominant, if this is true. All right. We were trying to illustrate potential games. Well, here's the potential function for that game. It is a potential game. And the potential function is very simple. It looks like this. Notice, so to verify that it is a potential game, observe that the payoff gain for player one, if his payoffs were given by the potential function, the payoff gain of choosing U over D would be 1 minus P1 if player two chose L. Notice that P2 drops out in the payoff difference, and his payoff gain would be minus P1 if player two chose R. Okay. And now, in fact, let's not worry about the algebra too much, but if we multiply it by, this was the term on the bottom of those probabilities, if we multiply this payoff difference under the potential by that constant, I'm going to get this constant times those payoff differences. But that constant times those payoff differences just gives these expressions here, which are precisely the payoff differences in the underlying game. Okay. So this is just to highlight that this risk dominance, which has cropped up all over the place, incidentally, risk dominance corresponds to being a potential maximizing equilibrium. All right. Now, what about the electronic mail game? I'm going to give you a verbal description of the electronic mail game. There are different formalizations that you can give. You can do it with partitions, you can do it with type spaces. It's a little involved just to describe it. I'm going to say it in words. Consider the following situation. Suppose there are two players who have to decide whether to invest or not invest. Suppose that if the economy is in a good state, invest and invest and not invest, not invest are both strict Nash equilibria. Okay, so yes, that's obvious. Okay. Notice that the risk dominant equilibrium in this example is not invest, not invest. Why is that the case? Well, if you're player one, you require a 2/3 probability for your opponent to invest in order for you to have a best response to invest. And it's symmetric. So both guys need a 2/3 probability of the other guy investing in order to invest. Whereas you only need a 1/3 probability for the other guy to not invest for you to have a best response to not invest. So the risk dominant thing is to not invest in this example. But if there was common knowledge that the state was good, clearly, our game theory tells us that either thing could happen. Either thing is a perfectly legitimate prediction. Okay, but suppose that there was another state of the economy. Suppose the economy might be bad, and in the bad state of the world, each player has a dominant strategy to not invest. This is a typo. Sorry. I will circulate the slides to you with the, no doubt, numerous typos, hopefully many of them corrected after the lecture. All right. Suppose the state of the economy is bad with a small probability, with probability epsilon. Think of epsilon as a small number, but the state of the economy is good with probability 1 minus epsilon. And now we're going to give you the information structure in words. What is the information that players are given about the state of the economy? Okay, and this is the email story. Messages get sent, messages get lost. Suppose that initially player one knows whether the state is good or bad, but player two does not. Player two has no idea. Okay, but if the state is good, player one sends a message to player two telling her that the state is good. Why not? Okay. Now, messages get lost, unfortunately. So if player two receives the message, she will send a confirmation back to player one saying that she got the message. Okay, so if player two receives a message from player one saying that the state is good, she sends a message back confirming that the state is good. But each message gets lost with probability epsilon. Player one's message, player two's message, and indeed, something got missed here. We assume also that they keep sending messages, which is a little pathological, I know, but that's the story. So player two sends the message to player one. If player one gets a confirmation from player two, player one sends a confirmation to player two that he received the confirmation from player two. Okay, so let's call it Ariel's paradox. No player will ever invest in the unique equilibrium of this game for any positive epsilon. Epsilon can be as small as you want, but for any positive epsilon, neither player will ever invest, is the argument. Player two, if player two knows that the state is bad, then obviously player two will not invest. So if player one knows that the state is bad, he has a dominant strategy to not invest, he will not invest. Suppose player two never receives a message. Okay, there are two possibilities. One possibility is that the state is bad and player one didn't send a message. The other possibility is the state is good. Player one sent a message, but the message got lost. Okay, now the state is much more likely to be good than to be bad. Okay. However, if you work out what's the probability she attaches to the state being bad, so ex ante, it's much more likely to be good. But conditional on never receiving a message, the probability she assigns to the state being bad, well, the ex ante probability of the state being bad is epsilon, and the probability of the state being good, but one's message getting lost, is 1 minus epsilon times epsilon. So the conditional probability that the state is bad is actually going to be more than a half. Okay? And if the probability of the state being bad is more than a half, the payoffs were fixed so that you don't have an incentive to invest. And the argument goes on, if player one knows that the state is good, he sends a message to player two, but he never receives a confirmation. What's he going to be thinking? Well, he's going to attach probability. So the ex ante probability that the state is good and his message gets lost is 1 minus epsilon times epsilon. The probability that the state is good and his message does not get lost, but the confirmation gets lost, is 1 minus epsilon squared times epsilon. Okay? But this guy is more than a half again. Okay? It's about a half for small epsilon. But that's enough to say that he must have a best response not to invest, because he knows that player two is never going to invest if she didn't receive a message. Okay? And so, okay? So player one and player two will never invest. And that's a paradox, maybe. So suppose the n messages get through. Both players know that the state is good. Both players know that both players know that the state is good, and so on. That's going to be true up to n times. But that argument that I gave says that no matter how many messages get sent, they won't invest. Okay? So neither player will invest in equilibrium. Okay? That's the paradox. This is a very artificial game. Our understanding of how higher order beliefs might matter in a game probably don't depend too much on your intuition about exactly what should happen in this game, or even maybe on experiments where you do exactly this game. The game illustrates a logic by which small probability events or higher order beliefs could matter a lot in determining what happens. Okay? I think higher order beliefs matter in practice. I want to see how that works. All right. So let me talk about robustness in complete information. So the email game suggests a question. Invest in the email game. It is an equilibrium of the complete information game, but we've just seen, thanks to Ariel, that equilibrium is very sensitive. What Ariel was highlighting was that it's very sensitive to the number of levels of knowledge. An infinite number of levels of knowledge meant one thing. Any finite number of levels of knowledge meant something different. That seems like an excessive sensitivity somehow. Also, the way I described it, actually that wasn't exactly how Ariel did it, but the way that I described it, it illustrates that a small probability event that the state is bad can have an arbitrarily large impact. It's epsilon probability that the state is bad. So one response to the email game is to say, are there equilibria that are not going to exhibit this type of extreme sensitivity? Okay? We might call those equilibria robust. They're not so sensitive. Okay? So this is the formal definition of robustness to incomplete information. So an incomplete information game consists of, for each player, a countable set of types. There's going to be a probability distribution over the set of types of the player. And there are going to be payoff functions. Each player is going to have a payoff function that says for every action profile and every type profile, what's your payoff going to be? That's an incomplete information game. Okay, we analyze incomplete information games in the usual way. So a behavioral strategy says for each type, what's the mixed strategy that that player is going to follow? Player I's interim utility, we can write down what's player I's utility if he is type TI, if he chooses action AI, he thinks that his opponents are choosing behavioral strategy, sigma minus I. Well, it's just going to be the relevant expectation. Here, I'm extending this utility function over, I defined it over action profiles, but I'm extending it over behavioral strategies. Okay, and we can talk about what a player I's best response is. So for a particular type, we can say if he thinks that the behavioral strategies of his opponents are sigma minus I, what are the set of actions that are going to be best responses for him? And you know the definition of Bayes-Nash equilibrium. Here we're writing down an interim definition of Bayes-Nash equilibrium. When is it the case that any action that's played with positive probability for player I, if he's type TI, is a best response for type TI against sigma minus I. I assumed countable types. One reason for that is that it ensures the existence of Bayes-Nash equilibrium. And what I'm going to be really interested in is not, this incomplete information is going to be something I'm adding in. But what I'm really interested in is what's the actions that get played, not how they depend on types. So I'm going to talk about the equilibrium action distribution of a distribution of actions is an equilibrium action distribution of the incomplete information game if there exists a Bayes-Nash equilibrium that induces that probability distribution over action. So we're integrating out. So this is not clear. This is incorrect. This should say the distribution over actions, if we integrate out over types, it should be this guy given TI and then summing over possible types. All right. Now, what I'm interested in is not just any incomplete information game. I'm interested in the idea that there is a complete information game, but I'm going to add in a little bit of incomplete information. So we're going to talk about elaborations. Terminology goes back to Freudenberg, Krebs, and Levine. An elaboration of the game is just saying we start with a complete information game, but we're going to add in the possibility of some incomplete information. So we can talk about standard types of the player in the incomplete information game, types whose payoffs are given by the complete information game that we started with. So in the literature, they're called standard types or normal types or unperturbed types. Call it TIGI is the set of types whose payoffs are exactly given by GI. Okay, but we allow for the possibility that there are some other types. These other types might have dominant strategies to play particular actions. We sometimes call them crazy types when they have dominant strategies to play particular actions. We can write TG for the product of the sets of standard types. This shouldn't be an intersection. This should be a product. Sorry. So this is the set of type profiles where everybody knows their payoffs are given by the complete information game. And we'll say that an incomplete information game is an epsilon elaboration of the complete information game if the probability of these standard type profiles is at least 1 minus epsilon. So an epsilon elaboration is close in an intuitive sense, at least, to the complete information game. We're interested in whether behavior is going to end up being close. Here is the definition of robustness and complete information. We can define, we have these action distributions. So so use this notation for the max distance, that is the greatest difference in probability for any action profile between the two distributions. And we'll say an action distribution is robust and complete information. If for any delta, there exists an epsilon such that any epsilon elaboration has an equilibrium action distribution that's within delta of the equilibrium action distribution we started with. Okay. This is the definition we used. People have tweaked the definition in various ways, depending on the question you're asking. There might be better ways to ask it. We have a recent note where we talk about strict robustness to incomplete information, which this is not a deep difference. It's just what gives cleaner answers. But this definition is a little extreme in that we're saying that the standard types have to know exactly what the payoffs are. A more reasonable definition here, we're allowing for the possibility that payoffs might be a little bit different with high probability. All right, so a risk-dominated equilibrium of a two-player, two-action game with two strict Nash equilibria is not robust. Okay, you already know that that's true because you saw the email game. Okay, so in the example, invest was a risk-dominated equilibrium. For any epsilon, we constructed an epsilon elaboration, and we could have done it for any epsilon whose Bayes Nash equilibrium had not invest always played. So that establishes that invest is not robust in that particular game. And in fact, you can do an analogous construction. For an arbitrary risk-dominated equilibrium, an arbitrary equilibrium of a 2x2 game that is not risk-dominant, you can do an analogous construction. So there's nothing to prove here. Okay. However, I can tell you that the construction that we did, the email construction, did rely on the fact that the equilibrium we were killing, that we were making impossible, invest, was risk-dominated. Okay. Put differently, the equilibrium that took over, the equilibrium that everybody ended up playing in the epsilon elaboration was risk-dominant. Okay. We were using that fact. We could not do a similar construction for a risk-dominant equilibrium. And indeed, you can show that the risk-dominant equilibrium of a two-player, two-action game with two strict Nash equilibria is robust. Okay, I screwed up my timing. I don't know what we want to do. I have material for 3 hours. I have material for 5 hours. But I also don't know everything. It's been flexible the material that I have prepared, so easy. Should I keep going a bit? Somebody has to decide for me.
個人的には助けてほしい。けど、他の皆さんがおったらいい。
At least there are some interest, so please keep going.
Okay.
Yeah, thank you.
Okay, so let me keep going for a bit.
You guys can leave if you are not interested in, but there are at least several people who are interested in. So
the paper with Atsushi we provide a generalization of risk dominance for many player, many action games and show that it's sufficient for robustness. Okay, slight change of pace here. I want to focus, so some results I'm going to talk about are going to specialize, and I want to just focus on a special class of games a little bit. So binary action supermodular games. So Daisuke and Satoru, and I with Daisuke and Satoru are writing papers about this class of games. I think it's an interesting class of games. So let me tell you about it. Okay, so binary actions means each player has two actions. We can call them 0, 1. I will sometimes call them don't participate or participate for the interpretation. Okay. So for a binary action game, a sufficient condition, the only thing that we care about is what is the gain that player I gets from choosing action 1 over action 0. So call that Fi of A minus I, that is the payoff gain, that is a sufficient condition for payoffs of the game. Okay, and to be supermodular, that means that Fi is increasing in A minus I. If more players choose action 1, then I have more incentive to choose action 1 myself. Okay, so this inequality, this is a vector of zeros and ones. So if the vector is bigger, then you have so it's set inclusion if you thought about it in terms of the sets of players who are choosing action 1. Okay. A special type of binary action supermodular game is a symmetric one. What do I mean by that? Think of a game where players are identical, permuting them doesn't make any difference. So that would say that the payoff gain that you get, given that your opponents are playing A minus I, just depends on the number of players who are participating, the number of other players who are participating. Okay, and I want it to be the same function for every player. Okay, and of course, to be supermodular, H has to be increasing in the number of players who. So an interesting fact is that all participate is the potential maximizing equilibrium of game G, which we also said was summarized by F. If it's the case for the symmetric one, if it's the case that the sum of these H of Ks for K taking every value between 0 and I minus 1 has to be non-negative. Okay. So what does this mean? It means that if you are playing such a symmetric binary action supermodular game, if your belief was uniform over the number of your opponents who are participating, you thought any number was equally likely, okay, Laplacian is a name we made up for uniform. So you have uniform beliefs over the number of players who are participating. That's a test of what the potential maximizing equilibrium is. So if it's negative, the potential maximizing equilibrium is nobody participating. Okay. So many economic problems have been modeled as binary action supermodular potential games. In particular, sorry, I should have said, okay, we define binary action supermodular games. If a binary action supermodular game is symmetric, it is a potential game. I should have said that. Okay, so the potential comes for free if it's symmetric. It doesn't come for free otherwise. Okay, so lots of economic problems have been modeled as binary action supermodular symmetric and thus potential games. lots of global game applications are about that. I would argue that many economic problems should be modeled as asymmetric payoff binary action supermodular potential games. Okay, potential has bite in general in an asymmetric game, but there are many potential games. They have a natural interpretation. What makes it a potential game? I think this is an interesting object of study. It's going to be a punchline in my lectures, actually. Okay. As I will explain later, maybe, characterizing what are the potential maximizing equilibria of asymmetric payoff binary action supermodular potential games is actually an interesting and quite challenging problem. It's a mathematically challenging problem to get a complete characterization. I think there's lots of interesting policy questions that would relate to answering this question. I'm ultimately going to be saying that potential maximizing equilibria gets selected. Okay, so
give us some example of the economic applications.
yes. Well, an economic application that I'll talk about tomorrow is there's a paper by Halleck, Litnowski, and Rappaport on team production. So suppose you have a set of players. Each player has to decide whether to exert effort or not. Each player has different cost of exerting effort. The probability of the project succeeding is a function of the set of players who exert effort. It's increasing in the set of players who exert effort. So that is an interesting economic problem that people study. And people also study what happens. So given that you can't observe that a player exerted effort, the only thing you can do is provide a bonus to an individual player. So post-bonus, it's still a binary action supermodular potential game. And if you wanted to say what's the optimal policy in that case, they have some results, but a complete characterization we don't have. That will be an example.
So that's binary action because either effort or shove up to.
Yes.
Okay.
Yeah. I mean, so if I think about what the applications of global games have been, there are lots of applications to political economy, revolutions. Do I want to participate in the revolution or not? That's a binary choice. Currency crises are often modeled as binary choice games. Do I attack the currency or not attack the currency? Bank runs. Do you leave your money in? Do you withdraw your money? These are the kinds of problems. All right. Okay, so the potential maximizing equilibrium of a binary action supermodular potential game is robust to incomplete information. Actually, a stronger result is true. Any potential so we don't actually need the binary action supermodular for this to be true, except that you have to tweak the definition of robustness a little bit if you don't have the supermodular payoffs. I'm not going to explain this, but so I'm interested in the binary action supermodular games, the potential maximizing observation is a lot more general. All right. Let me talk about a class of games which relate to global games. They're going to be global games, what are called global games. Think of them as a special class of elaborations that I'm going to talk about. Okay, particular structure of elaboration. So suppose we start from a binary action supermodular potential game. Suppose, and let me finish in 5 minutes or so, and we'll see what we do tomorrow. So suppose we start with a binary action supermodular potential game, complete information game. But suppose the common knowledge of payoffs assumption, the complete information assumption, is not something that we want to take too literally. Let's come up with an intuitive class of elaboration, not these big abstract class of Kaji and Morris. Let's come up with some intuitive class. Okay, so here's an intuitive class. Step one, let's introduce some uncertainty about payoffs. We're going to do it in 2 steps. So we're going to say, first, let's have some uncertainty about payoffs. So let's represent the uncertainty by a one-dimensional space theta of states of the world. Suppose there's a strictly positive smooth density on states of the world. And let's assume that players have payoffs for this incomplete information game. UI is player I's payoff function. Let's suppose that there is some state, call it theta star star, where payoffs are exactly given by G, but we're allowing for the possibility of other states where payoffs vary. Let's assume that we have that at every theta, we're talking about a binary action supermodular potential game. Let's suppose that the your payoffs are continuous in the state. Each player's payoffs are continuous in the state. Let's suppose that payoff gains are increasing in theta. So higher states make you want to choose a higher action. And let's assume dominance regions. What does that mean? Let's suppose that there exists a state, theta lower bar, such that every player has a dominant action to play action 0. Action 0 is a dominant action at every state below theta lower bar. And conversely, there's another state, theta upper bar, such that every player has a dominant action to play action 1 at every state. This is a typo, every state bigger than theta upper bar. Okay. And there are some additional technical restrictions that are made here. So suppose that is my uncertainty that I want to put into my elaboration. Let's also put in some asymmetric information. Okay, so let's say that each player, I'm going to say that each player is not going to know exactly what payoffs are, but they're going to observe a noisy signal of payoffs. So this is a particular incomplete information structure. They observe the state plus a noise term where there's a random variable epsilon I for player I, which has some density fi. And let's parameterize the amount of noise by nu. So I'll have a constant that I can increase or decrease to scale the amount of noise that players are observing. So thus players are observing noisy signals of the state. So now I have an incomplete information game parameterized by the prior that I put on states of the world and the scale of the noise by which players observe the state of the world. Okay. So here is a global games result. Suppose we define an object, which is AI star, which maps the state space or the real line to 0, 1, where we're going to have each player I switching from action 0 to action 1 at some critical threshold theta I star. And suppose these theta I stars are chosen in such a way that the action profiles at any theta, at any state, corresponds to the potential maximizing equilibrium of the complete information game being played there. Okay. Claim, suppose I look at a sequence of equilibria of this game. So that's saying I fix mu and I look at equilibria of the game indexed by nu, where nu is tending to 0. So a sequence of equilibria. I claim that the equilibria will be converging to these A stars up here. That is the cutoff. So you will be playing action 0. Player I will be playing action 0 if his signal is below that cutoff, and he will be playing action 1 if his signal is above that cutoff. That's what's going to be happening almost surely as nu tends to 0. So in words, as noise goes to 0, there's a essentially unique equilibrium where the potential maximizing equilibrium of the game is always played. Okay, now something to notice is that this is independent of mu. Okay, so the behavior in the limit doesn't depend on what the prior was. As long as the noise is going to 0, we're pinning down what's going to get played.
Can you remind me, why is the some elaboration? Because elaboration was defined on prior.
Yes, I will make it. I haven't done that bit yet.
Okay.
Yeah. So this is essentially, well, this is an application of the result of a paper that I have with Frenkel and Posner. Actually, let me skip this. We can talk. Frenkel and Posner does some more stuff, and let me come back and explain that tomorrow. But let me just sort of to answer your question, just say we can also think about this prior. Suppose the prior, let's now have a sequence of priors that are concentrating mass on the complete information game that we started with. So we can write epsilon hat of mu is saying that the prior is epsilon close to the complete information game if with probability at least 1 minus epsilon. Yes, sorry, this went off the end of the slide. So I want to say that the probability that payoffs in the incomplete information game are within epsilon of the complete information game, that probability is at least, we're missing here, 1 minus epsilon. Okay, so we're concentrating mass on the complete information game. So to make it like elaborations, we will be interested in sequences of priors where we're approaching the complete information game. And now it's going to be a corollary that you can look at the limit of what gets played, what is the distribution of actions that gets played if we consider the double limit where we take nu to 0. So the noise is going to 0, so we're getting the global game selection, but then we make the prior concentrate around the complete information game, and I assert that the behavior will correspond to the potential maximizing equilibrium of the complete information game. So let me stop. Maybe that's enough for today. I will be here at 10:30 sharp tomorrow, unless someone suggests that I come even earlier, we'll be happy to. But anyway, that's for tomorrow. Okay? Yes.
Okay, thank you, Stephen.